Definition and steps of Big M method. The Big M method is a version of simplex algorithm that is first finds a basic visible solution by adding artificial variables to the problem. The objective function of the original LP must be, of course, modified to ensure that the artificial variables are all equal to 0 at the conclusion of simplex algorithm. If an LP has any more or equal constraint, a starting PFS may not be readily apparent. When a basic feasible solution is not readily apparent, the Big M method or the two-phase simplex method may be used to solve the problem. The main here, Big M method is a version of simplex method. Usually, Big M method used to solve the problem of minimization. Here we have to put into account the importance or significance of slack, surplus, and artificial variables. We use slack and surplus variables interchangeably. S stands for slack variables, A stands for artificial variables. So we have to put into account the importance of using these two variables, the artificial variables and the slack variables. Referring back to the previous lectures, the transformation of constraints or conversion of constraints into equation by adding slack variables or subtracting slack variables is known as standard form. As we mentioned before, to convert the constraints or inequality to the standard form means to add or to subtract slack variables. In operations research, this is known as standard form. To convert inequality or constraint from the canonical form to the standard form. So the Big M method is another method of removing artificial variables from the basis. In this method, we assign coefficients to artificial variables undesirable from the objective function. If objective function z is to be minimized, then a very large positive price, for example called penalty is assigned to each artificial variables. Similarly, if z is to be maximized, then a very large negative price, also called penalty, is assigned to each of these variables. The penalty will designated by negative big M for a maximization problem and positive big M for a minimization problem where M more than 0. Now, the givens are big M methods is a form of simplex method, but mostly is used for solving the problem of minimization. In spite of it can be used to solve the problem of maximization. The difference between simplex methods and big M methods: if the big M methods are oriented to solve the problem of minimization, we will use artificial variables. We use artificial variables in case of minimization to compensate the negativity of a slack variable. Let me explain this phenomenon. If the constraint or inequality is more or equal, we have to subtract slack variable negative s. As we emphasized, all decision variables must be more or equal 0. In this case, s will be negative, less than 0. So to compensate the negativity of a slack variable, we have to add the artificial variables a. Number 1. Okay. Number 2, if the objective function is to be minimized, then a large positive M should be assigned to each artificial variables. On the contrary, if the objective function is to be maximized, the large negative big M assigned to each of these variables, this which we know as big M. Let's check the steps of applying the big M methods. Modify the constraints so that the right hand side of each constraint is non-negative. This requires that each constraint with a negative RHS be multiplied by negative 1. Remember that if you multiply an inequality by any negative number, the direction of inequality is reversed. After modification, identify each constraint as more or equal, less or equal, or equal. 3 versions of constraints. So modify the constraint so that this is as condition. You need to modify the constraint so that the RHS right hand side of each constraint, it must be non-negative. Okay. In order to reverse the constraint from type less or equal into type more or equal, we need to multiply this inequality by negative 1. Okay. The form of constraints are 3. Either the constraint more or equal, or the constraints less or equal, or the constraint equal. In our case, if the problem is about maximization, the corresponding constraint must be less or equal. If the problem about minimization, as mentioned before, the corresponding constraint should be more or equal. These are a conditions. Now, the second step, convert each inequality constraint to the standard form. If constraint I is less or equal constraint, we add slack variable Si. And if the constraint I is more or equal constraint, we subtract an excess surplus variable Ei. Add an artificial variables Ai to the constraint identified as more or equal constraint to the end of step 1. Also add the sign restriction Ai more or equal 0. So, generally the steps of applying big M methods is to fix the constraint to the standard form and to artificial transformation. What do we mean by artificial transformation? We mean by artificial transformation adding A stands for artificial variables, or subtract A. Okay. So the first step to convert the constraints or inequalities into standard form. by adding or subtracting slack variable. Then to transform the constraints into artificial step by adding or subtracting artificial variables. Let m denote a very large positive number. If the LP is a MIME problem, add for each artificial variables MA to the objective function before equal to 0. If the LP is a max problem, add for each artificial variable negative MA to the objective function before equal to 0. Since each artificial variables will be in the starting pages, all artificial variables must be eliminated from objective row before applying the simplex method. Then solve the transformed problem as simplex by choosing the entering, leaving variables and key element. Remember that m is a very large positive number. M is a very large positive number. This is about to make the objective function zero equation. To make the objective function zero equation. In case of minimization, we will transform the objective function to the equation or zero equation by subtracting the slack variables negative s, adding coefficient to slack variables equal 0, and by adding artificial variable a with the coefficient equal big M. Remember, the sign of the coefficient of s equal negative 0 and the sign of the coefficient of a equal positive M. Actually, big positive M. This is the main here. Okay, express the LPP in the standard form by adding slack variable, surplus variables, and artificial variables. Assign a 0 coefficient to both slack and surplus variables, and a very large positive coefficient plus M for min case, and negative M for max case to artificial variables in the objective function. Secondly, the initial basic visible solution is obtaining by assigning 0 value to original variables. calculate the value of Cj minus Zj in last row of simplex table and examine these values. If all Cj minus Zj more or equal 0, then the current basic feasible solution is optimal. If for a column K, Ck negative Zk is most negative and all entries or all entries in this column are negative, then the problem has unbounded optimal solution. If one or more Cj negative Zj less or equal 0 minimization case, then select the variable to enter into the basis with the largest negative value, that is Ck negative Zk minus Cj negative Zj to Cj negative Zj less or equal 0. Okay. In details, here we would like to break down the previous mentioned steps. Express the LPP linear programming problem in the standard form. By adding slack variables S and artificial variables. Assign a zero coefficient to slack variable and very large positive coefficient plus m for minimization case and negative m for maximization case to artificial variables in the objective function. Now we face two steps. First step concerning with transformation of the objective function, making the objective function zero equation. By adding slack variables with the coefficient 0 and subtracting artificial variables. This is in case of maximization. Otherwise, in case of minimization, we will convert objective function to zero equation by subtracting slack variable S with zero coefficient and adding artificial variables with the big positive m coefficient. Okay? The initial basic feasible solution is obtained by assigning zero value to original variables. Okay. Then we are going to calculate the value of Cj negative Zj in the last row or the row of simplex or the row of objective function and examine this. Now, let us state this case. when we dealt with the simplex method, the iteration of the solution must lead to the last situation when there is no negative value in the row of Z. The disappearance of the negative value of the row of Z means that we obtained the optimal solution. Okay. In case of big M methods, the disappearance of positive value means that we obtained the optimal solution. Given the various cases, in case the differences between Cj and Z more than 0, then the current basic feasible solution is optimal. Otherwise is unbounded in case of negative, or less than 0 is no more than 0. Then select the variable to enter into basis with the largest negative Cj negative Zj value. It will be very clear in the practical process of application. Okay. For determine the key row and the key element. Key row means that leaving row, exiting row. Key element means the pivot element or key element, in the same manner as discussed in the simplex methods or simplex algorithm of maximization. So the division of the column of constants over the column of the entering column, and the intersection point between the leaving row and entering column. This is a point is known as pivot element or key element. Let's see some remarks here. At any iteration of simplex algorithm, any one of the following cases may arise. If at least one artificial variable is present in the basis with zero coefficient of m, in each case Cj negative Zj less or more or equal 0, then the given LPP has no solution. That is, the current basic feasible solution is degenerate. 2. If at least one artificial variable is present in the basis with the positive value and the coefficient of m in each Cj negative Zj more or equal 0, then given LPP has no optimum basic solution. In this case, the given LPP has no pseudo optimum basic feasible solution. First example, solve the following LPP using penalty, big M method. Okay. Given min z equal 20x1 plus 30x2 plus 16x3 is an objective function concerned with the problem of minimization. Twenty is the coefficient of x1, refers to the cost of one unit of x1. 30 is the coefficient of x2, points the coefficient points the cost of one unit of x2, and 16 is the coefficient of x3. This objective function is the subject to 2.5 x1 plus 3x2 plus x3 more or equal 3, and the second constraint is x1 plus 3x2 plus 2x3 more or equal 4. The non-negativity condition is x1, x2, x3 more or equal 0. So the givens are 2. The objective function is minimization function. Very good. Number 2, the corresponding constraints are suitable. The two constraints are more or equal. Now, what is the first step here? Is to convert inequalities or constraint into the standard form by subtracting surplus or slack variable s and adding artificial variables a. A is more or equal 0, not equal 0, actually more than 0. Now the new constraints will take the following shapes: 2.5 x1 plus 3x2 plus x3 negative s1, s1 is the slack variable, plus a1, the first artificial variable, equal 3. The second constraint is x1 plus 3x2 plus 2x3 negative s2 plus a2 less or equal 4. 3 and 4 are constants. 2.5, 3, 1, 1, negative 1 and 1. These are the coefficients of variables of constraint 1. Then 1, 3, 2, negative 1, positive 1 are the coefficients of the second constraint, equal 4 is the constant here. Let's see the next slide. To the second step, we are matrixing, between brackets, we are matrixing the equations. This is a form of matrix. Let's look. 2.5, 3, 1, negative 1, 0, 1, 0. These are coefficients of constraint 1. 1, 3, 2, 0, negative 1, 0, 1. These are the coefficients of constraint 2. x1, x2, s1, x3, s1, s2, a1, a2. These are variables. And 3, 4 is constants. These are constants. Step 3, to convert z or objective function to zero equation. So to take the terms from the right side to the left side, and we capture that. We capture z negative 20 x1, negative 30 x2, negative 16 x3, plus 0 s1 plus 0 s2 minus ma1 minus ma2 equal 0. Now the first steps is to design the primal table. Primal table consists of 4 rows and 9 columns. The upper row represents the non-basic variable. Non-basic variable x1, x2, x3. The cells inside the cells for the row 1 are the coefficients of the constraint 1, while the cells for the row 2 are the coefficients of the constraint 2. So 2.5 is the coefficient of x1 in the constraint 1. Respectively, 3 is the coefficient of x2, 1 is the coefficient of x3, negative 1 is the coefficient of s1. Constraint A has no s2 and has no a2. That's why it's 0, 0. 1 is the coefficient or parameter of a1 in the constraint 1. So also 1 is the coefficient of x. 1 constraint 2, 3, 2, 0, negative 1, 0, 1, 4 respectively. Negative 30, negative 20, negative 30, negative 16, 0, 0. Negative m are the coefficients of z. Check z, the zero equation of z, or the zero equation of objective function. Remark, the coefficients of the objective function are negative, and the coefficients of the artificial variables are negative and big. That's why it called big M. The deletion of the negativity is required to find the optimal solution. To solve the mentioned problem, we need to apply the following formula. What that mean? If we are planning to find the optimal decision, the negative value in the row 3 must disappear. To disappear these values, the negative value in the row 3, we need to apply the following formula. Okay, the mentioned formula in the previous slide states that M multiplied by between brackets R1 plus R2 plus R3. This multiplication R1 plus R2 brackets multiplied by M plus R3. Now we are going to apply this formula vertically, looking at the table, primary table, vertically. So 2.5 is the coefficient of x1, where in the row 1, and 1 also is the coefficient of x1 but in the row 2. R3 is lower row. So these figures 2.5, 1, negative 20 are coefficients of x1. All of them are the coefficients of x1. The result would be 3.5 m negative 20. 3.5 is 7 over 2. So is 7 m over 2 negative 20. M times 3.3 negative 30, it is 6m negative 30, and 3m negative 16, m multiplied by brackets negative 1 plus 0, it is negative m, m multiplied by 0 negative 1 plus 0, it is negative m, m multiplied by 1 plus minus 1 is 0, m multiplied by 1 plus minus m is 0. The last is m multiplied by 7 plus 4 is 7m plus 0 is a 7m. So now we applied this formula in order to escape the high negativity of the values in the row 3. Now the second step is to assume very big number for m. Very big number for m. Why very big number for m? Because our aim to change the negativity of the values of that to positivity with the high coefficients. This is our target. Let's see our harvest in the next slide. Table 2. we copied the result of the previous formula and we pasted it here. Okay, 7m over 2 negative 20, 6m negative 30, 3m negative 16, negative m double 0, and 7m. So now we are going to apply the main steps. Okay, first, to determine the entering variable, we need to assume biggest, very big number for m and let it be 100. We assume that m equal 100, and to find the positive value, to convert this negative value to what? To positive value. So 7 times 100 over 2 negative 20 is 330. So that's correct. Let's move to the second column x2. 6 times 100 negative 30, the remain is 520. And the last here we are focusing on the basic variables, non-basic variables in this case, x1, x2 and x3. S1 and S2, A1 and A2 are artificial or slack variables. Don't worry. So 3 times 100 negative 16 equal 284. So the biggest positive value is 520, which faces x2. Then x2 is an entering variable. In case of minimization, the entering variable, the key variable, the entering column, that variable which faces biggest figure, the biggest number in the row 3 or row Z. We use, so x2 is set to be entering variable because it faces biggest figure in the row 3 equal 520. We determined entering variable. We have the formula which mentioned before, m r1 plus r2 between brackets plus r3. D'accord? Second step is to point the leaving row. So to point the leaving row, just look to the column of constants, cons, and the column of x2 or entering variable. Divide the column of constants over the column of x2 and find the least result of this operation. Then point where the least result has happened. Okay, check. 3 over 3 equal 1 ratio mine, and 4 over 3 equal 1.3, equal 1.3. So RO1 is said to be leading variable because it got least ratio of division. So then the row has the least ratio is said to be the leading variable, which is A1. Okay? Which is A1. Then R row 1, or between brackets A1, is the leading variable. X2 is entering variable. The intersection point between R1 and X2 is said is pivot element or key element. This 3 is the key element. Intersection point between row 1 and column X2. Then in the next slide we are going to determine what, or to find the pivot equation. The pivot equation equal R1 over key element or pivot element. D'accord? Okay, referring to the previous table, the key or pivot element is an intersection point between row 1 or A1 and column X2, or between leaving and entering variable. This key or pivot element equal 3. To determine the key or pivot equation, this is the main equation, plays significant role in the process of finding optimal solution. To determine the key or pivot equation, we need to divide row 1 over pivot element. The coefficients of A1 or row 1 are 2.5, 3, 1, negative 1, 0, 1, 0, 3. This over 2. The result is given 5 over 6, 1, and 1 over 3, and negative 1 over 3, 0, 1 over 3, 0, and 1. These values will be considered as the values of x2 in the next table or instead of A1. Okay. 5. The entrance of x2 as basic variable leads to the following change in row 2 and row 3. So R1, R2, and R3, or row 1, row 3, and row 3 represent A1, A2, and Z respectively. PE stands for pivot element and PEQ stands for pivot equation. That's all. The first iteration of the problem, we need to examine the change in row 2 AO2 or the change in row 3 O3. Okay. This is iteration. There is iteration. Row 2 or O2, the impact of the entrance of x2 as basic variable on A2 and Z. Okay. To check these changes, we are going to design two tables, one for A2 and the other for Z. So now how to find the new R2 or the new A2? So we need to formulate three rows. First row, the upper row for A2, the original A2, the values of A2, the coefficients of the row 2, and the second row is the pivot element of A2 multiplied by the pivot equation. Pivot equation is given, and the pivot element of A2 is the intersection point between the entering variable and A2. Okay. So we are going to copy the values of A2 as it is from the previous table and paste it here. Then we are going to find the result of multiplication. These results should be subtracted from the original A2. The new A2 is given -3 over 2, 0, 1, 1, -1, -1, 1, 1. These values should be the values of A2 in the next table. Also, we are going to do the same, to repeat the same procedure to find the new R3 or the new Z. So the first row in this operation represents the values, the original values or coefficients of row of Z, and then the next row is multiplication of the pivot element of Z by the pivot equation, and the result is given. And new Z is the result of subtraction row 1 by row 2. So we found out this -3 over 2 plus 5 0 m -6 m -10 m -2m plus 10 0 and m plus 30. Table 3 or iteration number 3. So this table includes x2 as the basic variable instead of A2, and the new A2 impacted by the entrance of x2 as basic variable, a new z impacted by the entrance of x2 as basic variable, we are going to follow the same procedures to determine the entering variable and leaving variable by assuming m equal 100, then negative 3m over 2 plus 5 equal 145, and m minus x equal 94. As mentioned, the entering variable must face the biggest positive value in the row 3, respectively x1 is rejected and x3 is accepted and a2 is leaving variable. So this operation ensures that a1 is entering variable, a2 is leaving variable, and negative 3 over 2 is key element, and the pivot equation is a2 over pivot element. Sorry, that's correct. That is correct. Iteration 4. So the following steps explain the changes resulting from the entrance of x3 as basic variable in x2 and z. We are going to follow the same previous procedure to calculate the changes in x2 and z. The new x2 at the result of entrance of x3 as basic variable, and the new z at the result of the entrance of x2 as basic variable is shown. We apply the same previous procedure to find these changes. Okay, the last iteration, table 4, shown R1x1, R2x3, R3z. Looking at the last constant column, the value of x2 equal 2 over 3, the value of x3 equal 1, and z equal 36. Okay, the iteration is said to be finished. Since there is no positive coefficient in the row of z, the iteration is said to be stopped. An optimal solution is presented where x1 equal 0, there is no x1, x2 equal 2 over 3, x3 equal 1, and s1 equal s2 equal 0, a1 equal a2 equal 0, and z equal 36. Let's try to check the proof of our findings. Return back to our constraints, where the first constraint is 2.5x1 plus 3x2 plus x3 negative s1 plus a1. There is no x1, that means 2.5 times 0 plus 3 times 2 over 3 plus 1 plus 0 equal 3. Correct, proved. The next constraint is x1 plus 3x2 plus 2x3 negative s2 plus a2 equal 4. Once x1 equals 0 plus 3 multiplied by x2, x2 equal 2 over 3 and plus 2 multiplied by 1 negative 0 plus 0 equal 4. Proved. And z equal 20x1 plus 30x2 plus 16x3. x2 equals 0. 20 times 0 plus 30 times 2 over 3 plus 16 over 1 is 36. And that is okay. It is proved. It is proved.